I don't know most of you. So how many people here are not cross-country pilots? Okay. That's not cross-country pilots because you're late starters, or not cross-country pilots because you're really young. Excellent, that's what we need. On the way to cross-country pilots though, or not going to do that? Try. Okay, brilliant. Deferred gratification is the name of the game with gliding. It isn't easy, and it takes a while to get up there. Okay, how many people here have got a gold C? Gold C. Diamonds? Anybody done 1,000K?
No.
You're after it. Wave soaring experience. How many are wave soaring pilots? Okay. Mountain soaring pilots? Mountain thermals? Okay, okay. So there's quite a few really experienced people here, and there's a few on the way up. And I don't get the impression that there's many competent cross-country pilots who are not wave or mountain pilots. Who's a competent cross-country pilot, does a lot of cross-country flying, but doesn't do wave or mountain? Okay, so well, you're going to learn, aren't you? You're stuck right here in the hot spot. So back up. Okay, just give you an introduction to myself. I've been doing this since I was 20, professional since I was 30. I've done the thick end of 14,000 hours. I've flown in Scotland, Wales, England, France, Germany, Spain, Lithuania, Poland. I've flown all over Europe. I've flown in Japan, America, in the mountains, in the flatlands. I've done a lot of flying in New Zealand, and a lot of flying in Australia. So I've kind of lived. I'd retired when I was 31 and started being a professional glider pilot instead. And I retired from being a piano teacher. So teaching glider pilots wasn't particularly hard after teaching children, you can imagine. And it's a skill thing, and it's a performance thing. And we'll talk about performance later on. Performance psychology is interesting. Anyway, that's me. I've been really lucky. I've been all over the place, and I've learned at the expense of my students. I've sat in the back of the glider and learned how to fly cross-country better through flying with students who've done it wrong. And I've learned through talking about it. When I was working for the BGA, I'd do a soaring course, and I'd go to, I don't know, sleep or somewhere. And Monday it would rain, Tuesday it would rain, Wednesday it would rain, Thursday it would blow its tits off, Friday it would rain. And you'd just spend all week in the briefing room working out ways to keep people happy and talk. So that was kind of my grounding in doing this kind of work. And then working at Amarama, we had great weather, but it didn't start until after lunch. So every morning we'd do weather, briefings, go fly. The next day we'd do weather, debrief, brief, fly. So I've had lots of time standing up. As a result, I know pretty well most of what I'm talking about, and I don't do any real prep. I like to talk off the cuff because it's more real that way. And sometimes I'll go down blind alleys and do the wrong thing, but usually it works out. Because I do that, it's quite nice to have a bit more of a conversation, a bit more of backwards and forwards. So it's good to get feedback. What I thought I'd talk about, we've got wave here, and given where we are in relation to the sea and the water down there, clearly you're going to have a lot of sea breeze effect. So we need to talk about wave, we need to talk about convergence. We need to talk about mountain thermal. When you get into the hills, you need to work out where the thermals are going to come from. Once you get into mountain terrain, almost the defining feature of mountain terrain is that it's a bit more reliable in terms of where the thermals are coming from. It's not like a completely uniform flatland where you fly in the Hay Plains going out of Benalla, you go north of the Hay Plains and it's like, might as well be a car park 50 miles across by 50 miles. It's completely flat. Where are the thermals? Well, the thermals are where the cellular convection organizes the thermals. So there's a thermal here, there's a thermal here, and there isn't a thermal here because there's a thermal here and a thermal here. Cellular convection, it has its own pattern. You fly in the mountains, get the thermal coming up the valley, coming off the ridge and popping off the top, because valley, mountain, ridge, that's the shape of the ground. It makes the thermals be in certain places. If you go to the mountains, you can more usually predict where the thermals are going to come from, which is great, given the difficulties of flying in the mountains. Anyway, I wanted to look at those subjects, how ridges work, how thermals work, how mountain soaring works, how wave works, how convergence works. And over the next few days, build an understanding and build, if you like, a language for talking about it. So those of you that are experienced have more ways to disseminate your experience to the less experienced people you rub up against, because that's the way we learn. You know, you hang around with people that know, and they talk to you, and you learn from them. So the more language that you have, the more ways of describing stuff you have, the better. And for the less experienced, it's a bit of a primer in how to soar. So the first thing I wanted to talk about was why, when you're flying the ridge, sometimes the ridge is really good, and sometimes it's not, despite the fact the wind's still blowing on it. And when the wave is waving, sometimes the wave sits right over the ridge, and you can climb up the ridge and climb off the front of the ridge straight into the wave. And sometimes the ridge is just a complete mess, and it's what we call out of phase with the wave. And you can't get very high on the ridge, and it's horrible on top and really difficult to get. And the wave sits well forward of the ridge, or well backwards from the ridge. I want to talk about that. Meteorologists, real meteorologists, don't use the T-phogram that much. They just use mathematics. Like real glider designers don't use the McCready generated polar curve speed to fly thing very much. They use maths and spreadsheets. We use the McCready diagrams, the polar curve and the drawing the tangent, to describe our glider's performance and to talk about it to other people. We use the T-phogram to describe the weather and to talk about it to other people. And the T-phogram is a much maligned diagram and rather misunderstood. But we need to get just a little bit into that to talk about stability, to talk about why the ridge works and why the ridge doesn't work. So let's draw some diagrams to start with to illustrate really what I'm talking about. So you're fortunate here in having decent sized ridges. Sometimes the flow is like that. And you can fly your glider in the lift zone up and down the ridge and get higher and get higher and get higher. And you can climb up well high. How high is the Bishop? It's 1,000 feet. And how high would you be able to get in non-thermal conditions on a good day? A couple of thousand feet. Okay. And sometimes the flow is not like that at all. You might recognize this. Oh, that wobbles backwards and forwards when I do that. Yeah, it does. I thought it's got a sudden flash of dizziness because it was going backwards and forwards. Sometimes the flow is like this. Sometimes the flow is like that. Sometimes the wind humps up in front of the ridge. You'll know that on a wave day because you'll see rotothermals out here and waves behind the hill. Rotothermal sitting in front of the hill, not over the hill, in front of it. And on a day like that, you'd say, oh, the wave is out of phase with the ridge. The wave's up here somewhere. We're talking about ridge soaring now, not wave soaring. And what controls this flow? It's the stability of the air. It's the stability of the thermal layer, the mixing layer, what we call the mixing layer or the boundary layer. It's the stability of this layer that controls the flow over the ridge. So in order to talk about the flow over the ridge and about ridge soaring safely and effectively, we need to start by talking about stability, because if you don't understand stability, you won't understand what's going on. So, stability. The T-phi is a little misleading because the T-phi as a diagram is a very distorted diagram. The way the axes work is terribly distorted. So let's just talk about stability and heat to start with. We know about atmospheric pressure. Atmospheric pressure is the weight of the atmosphere, each bit of atmosphere pressing down on the white, bit below it, bit below it, bit below it, bit below it, till down at sea level you get up to 1 bar, about 15 psi, give or take. And we know about heat. When you talk about temperature, what you're talking about is the energy imparted by the molecules bouncing around. Temperature is to put it really crudely, it's the number of impacts. If you stick your finger in a bowl of hot water, it's the number of impacts of atoms that bounce, molecules that bounce off your finger in any period of time. And that's a really, really crude way of putting it. Some models are inaccurate and some models are more accurate, but most models are useful, right? Hopefully the model is useful. The further apart those molecules are, the less energy you contain in a volume. So a volume of air down at sea level, 15 odd psi, a kilo of air, a cubic meter of air is about a kilo of air, 1.2 kilos, something like that. That volume of air has so many atoms in it, all bouncing around. You take a volume of air on the edge of space, you might have just like one atom, or two, or 100, or 1,000, as opposed to several billion. I don't really care about the numbers. A few atoms, a few molecules can only transmit so much heat energy. The atmosphere is warm at the bottom, cold at the top, right? Essentially, it's warm at the bottom and cold at the top. Also, the pressure increases as you go down, reduces as you go up. That's a gravity-driven thing. Pressure is caused by gravity. And if you look at all I don't do math, I'm blind to math. I can't do math. I can do words, but I can't do math. If you look at the equations that people use to describe the behavior of atmosphere, they've all got a little G in somewhere. Okay, so pressure and gravity are related. Pressure and heat energy are related. If we take a 1 meter cube of air from sea level, just take a box of air, put it in a really, really, really fragile rubber bag, really stretchy rubber bag, a balloon. If you lift it up, it's going to expand because the pressure is less. The heat energy that is in this 1 meter cube is going to be distributed through a larger volume. Each bit of it is not so warm. The temperature goes down. The energy density goes down, as well as the density of the gas. You've spread out the same energy in a bigger area. So we can graph that. For the bottom of the atmosphere, we can graph that. Take the use of color. The people that taught me to lecture used to say, use of color, G, use of color. Take a box of air from, I don't know, 10,000 feet. Take it down, that box of air will get compressed and the temperature will go up because you've got the same heat energy in a smaller space. Take it up and the temperature of the air will go down. Oh. I'm out of practice at drawing diagrams. Just wait one, hold with me. Use of color, neutral color, G. Take it upwards and the box of air will expand and the amount of heat energy per unit volume is smaller, as are the number of molecules per unit volume. This is denser, this is less dense, this is less dense. That's the way the atmosphere works. And this is called adiabatic heating and cooling. Who knows what adiabatic means? Not many. Adiabatic means that you're not talking about heat exchange with the surroundings. It's bicycle pump physics. You know, you squeeze a bicycle pump, the pump gets hot, doesn't it, in your hands? You fill the bicycle tire from a CO2 cartridge. Have you ever done this and got your fingers stuck to the cartridge because it gets so cold so quickly? Okie dokie. So this is actually the basis of what we need to know about a T-phogram, because the T-phogram describes this in such a way. Adiabatic heating and cooling, if you don't have heat exchange with the surroundings in the bottom part of the atmosphere with no cloud forming or evaporating, that line goes up and down and the temperature change is 3 degrees per 1,000 feet. That's the slope of that line. That's a constant in the atmosphere. There is a problem with the T-phogram. There's a problem with drawing the T-pho. Can you pull up the T-pho? Oh, sorry, excuse me. It's actually, so I can't see it from here. These lines here and here and here are the temperature axes. The temperature axes on the normal presentation are skewed across like this, because if the temperature axes weren't skewed across and you did a temp trace, a temp profile, it would be looking something like that. It just falls off to the left-hand side of the page so low, so quickly that you can't really see what's going on. And all the lines in the T-phi end up down here if you don't skew the temperature axes, okay? So we call the T-phogram, we call it skew T. It's called a skew T. Skewed temperature lines. And you skew the temperature axes, bend the temperature axes off to the right. So all the lines stand up, and then you can see the dancing worms, you can see what they're up to. The other part of the T-phi which is distorted is the pressure field. Look at the height, regular here. Look at the numbers here. It's a logarithmic pressure scale. I might not, it should be logarithmic on this one, but the pressure scale is distorted so that height can be seen visually as being linear up the graph. And if you do that, then you can end up with a set of lines going from there to there to there to there to there, which are the temperature axes. And these lines here represent the dry adiabatic lapse rate. Now, we need to think about the dry adiabatic lapse rate because we need to think about what happens in thermals, we need to think about what happens in wave, we need to think about what happens in convergence. We know that if we start a thermal off here, therefore, and it rises up, it will cool, and we'll call it the dry adiabatic lapse rate. We know that. When we're ridge soaring, we're not thinking about thermals, but we need to think about the quality of the mixing layer. If you have thermals starting off in the morning, or if you have a bit of wind and you have mixing, mechanical mixing of the air mass, then it's going to settle down at this arbitrary slope of 3 degrees 1,000 feet. This is what happens in the mixing layer when you just stir the air mass up. It will sit there at a lapse rate of 3 degrees 1,000 feet. It won't do it overnight because it's not being stirred up overnight. Generally, you get a decouple between the wind and the lower levels, And also, there's no sunshine to stir it up through convection. But during the day, you end up with thermals and wind, and it all mixes up. And the bottom part of the atmosphere, the mixing layer, ends up sitting at 3 degrees to 1,000 feet, which is bare. That's a prediction for the bottom layer of the atmosphere. Well, okie dokie. If you put a ridge in this, let's draw some wind. With the wind scale, let's draw some westerly. 20 knots of westerly, northwesterly. What's the best wind direction for the Bishop?
Southwest.
Okay, let's draw 20 knots of southwesterly then. Let's be consistent. Because I've never flown out of here, I don't bloody know. It's just this big lump of hill that I can't see properly from here. So let's draw this diagram, and let's say we've got a deep mixing layer and we've got a hill here. So there's no stability in this MS. If I take a parcel of air from here, say 500 feet above the ground, and I lift it up to be 1,000 feet above the ground, it's going to expand and it's going to cool. That's fine. The whole air mass is mixed up. This is at the same temperature of the air mass around it. The same temperature as the air mass off the hill. So here's a hill. No, I'll tell you what, here's a hill. Here's a hill. Well, the desk is a hill, right? The air mass starts here and it flows up, and as it flows up, pressure reduces, it cools. But the whole atmosphere, up and down here, and up and down above the hill here, it's all at the same temperature because it's all just getting mixed up. It's all sitting at a 3 degree per 1,000 feet slope. So that is straightforward. When it's like this and the air is not stable, has no stability, then the hill just works mechanically to deflect the flow, and you get a big deflection of the flow right up over the top of it. So in these conditions, you'll get the sort of flow over the ridge that Reitman describes, which is where you get lift going forwards and out from the ridge quite high. Straightforward. That's what you expect, that's what you like. And of course, if there are thermals being generated, let's put a thermal in the flow here. Let's generate some heat here that's going to become a thermal. It's quite a small diagram, isn't it? So let's say we have a little super adiabatic layer. Do we know what super adiabatic layer is? Okay, when the sun comes down and hits the ground, and it's the ground that heats the air. And the air gets a little bit warmer than the surrounding air mass. So suddenly, in that particular location, the temperature profile suddenly is super adiabatic. It's warmer than it should be, but it hasn't moved yet. The thermal won't, how much temperature does there have to be? How much extra heat does there have to be before the thermal moves? 0.01 of a degree, 0.1 of a degree, 1 degree, 10 degrees, 100 degrees, 1,000, you know, what order of magnitude? It's like a degree or 2 or 3 and the thermal will start moving. So to start with, you have a mixed layer, and then there's a thermal just about to pop up. If you do a little local sounding, you'd see a superadiabatic layer. That's the superadiabatic. So the sun cooks the thermal, and the thermal warms up. Anybody got a guess at the mass of your average British thermal?
30,000 tons.
It's more.
Scottish
Good point, well made. I was trying to get away from the, you know, Scotland has really small, nasty little thermals thing. The average British thermal, which is for the handicapping. It's a cylinder half a mile deep and quarter of a mile across. You take a cylinder half a mile, quarter of a mile across and half a mile deep. So that's 1,500 feet by 3,000 feet. That's the size of the British Standard thermal, and that is an 80,000 ton package of air. So I think the Titanic was about 50, 60,000 ton boat. It's a lot of air mass. Of course, the bit of the thermal you want to be in is not half a mile deep and a quarter of a mile across. It's more like a few hundred yards deep and a couple of hundred yards across. It's a tiny part of that overall circulation. Anyway, the thermal's heating on the ground. You've got 100,000 tons of air, give or take, sitting on the ground. It takes a while to accelerate and get going. It just has to gather and start to flow. And we'll talk about that later. But meanwhile, it's a superadiabatic layer. It's heating, and it will take off at a temperature which is somewhat warmer than the mixed atmosphere around it. And if this is mixed and has neutral stability, this is always going to maintain the slightly warmer. Okay. And it will go up until something changes with this profile, and we'll talk about that in a moment. So in this situation, if you've got a deep mixed layer well above the top of the hills, then you're going to get a flow which is like this, and the thermal comes through here, and eventually, we haven't talked about the formation of cloud, but later on we will. That's what you hope for in a ridge and thermal soaring situation. So if the top of the hill is 1,000 feet and the thermals are making cloud at 3,000 feet and topping out at 3,500 feet, that's a representation of the flow. Well, very nice. And that's easy to work with. So we can talk about flying in this and flying in thermals in this situation, and we will. But I want to talk about what's happening when it doesn't work like this. The bigger the mountains get, the more you have a chance of it not working like that, because you more chance you have of the mountains sticking into an inversion. So what is an inversion? At the top of the mixing layer, where the thermals stop, above that, the atmosphere doesn't like to convect. It will sometimes, but it doesn't like to convect. Generally, the flow is stable. The flow is laminar. The air mass is not mixed, and the average lapse rate for the whole atmosphere is approximately 2 degrees per 1,000 feet. Not 3 degrees per 1,000 feet. It's 2 degrees per 1,000 feet. And that's the average given what the weather does to the atmosphere. We can do a sounding, and we can say that today, because we've got, say, a high pressure flow, a high pressure system, and the high pressure is causing the air to come down and warm, you might do a sounding and you might find that the lapse rate is actually like this, and then the air stops getting colder with height. It might even get warmer with height. Strictly speaking, an inversion, I believe, describes where the air gets warmer with height. But we have a bit of a skew-if sliding scale here, because we know that in a mixed atmosphere, it's always reducing in temperature to 3 degrees per 1,000 feet. If it reduces by less than 3 degrees per 1,000 feet, glider pilots will call that an inversion. It might be an isothermal layer. That means it's the same temperature. It might be a slight reduction in the lapse rate. It might even get solidly warmer with height. It might even be a proper inversion. How do you get an inversion? Sea breeze will cause an inversion. High pressure system will cause an inversion. And One of the major causes of inversion is at night, the ground radiates the heat away into space, and then the ground's really cold, and the air next to the ground gets really cold. So it causes an inversion by bringing the temperature here right down. And there, first thing in the morning, there's an inversion. We'll talk about that later. So we're going to talk about a day when you have a T-phogram that looks like this, with what you might call a nose of stability. A nose of stability. So think about taking a parcel of air up and down here. This parcel of air going up and down gets smaller and gets bigger, but the temperature is always the same as the air around it in the mixing layer. Now take a parcel of air from here in a stable temperature profile. If you take this air down in a stable temperature profile and you heat it at 3 degrees 1,000 feet, and you take it down to here, suddenly it's warmer than its surroundings. And if you take this parcel of air upwards from this stable layer, take it up from its stable layer, suddenly it's colder than its surroundings. That's what a stable layer means. So a stable layer, grab a lump of air, pull it down, it heats, and it's warmer than the air around it. Let it go and it springs back up again. We'll talk air buoyancy and temperature. You know about thermals being buoyant. That becomes a thermal and springs back up again. Take a piece of air from the stable layer, lift it up, and it'll be cold. And it'll be colder than the air around it, let it go, and it'll bounce back down. So the nature of the atmosphere is when you take a parcel of air, you drag it up and you drag it down, it'll heat or cool by 3 degrees 1,000 feet because of adiabatic heating and cooling, because of pressure, because of gravity. What it does when you let it go depends on the surrounding air, the air surrounding it. In the mixed layer, you can pull it up and down. There's no resistance because it's always going to stay at the same temperature as the air mass because the air mass around it has all been up and down. So it's all at the same temperature for whatever height. Stable layer, take a lump of air in the stable layer and move it, and you'll generate a temperature difference between the air you've moved and the air you haven't moved. What happens when the ridge is sticking into a stable layer? That's a problem. So let's redraw this from scratch and draw a situation where the ridge is sticking into a stable layer. So this is right at the heart of soaring in terrain, where you have wind and you have terrain sticking up into the atmosphere. If you fly at a narrow mine or Benalla, you just don't ever think about this stuff. You don't need to. All you ever think about is this, you know, is there going to be clouds, and this, what's the wind doing? Let's draw a mountain sticking up into a stable layer. So there's a little bit of thermal activity. Maybe this is, say, 4,000 feet tall. And the thermals are going to say 2,000 feet. And there's a bit of a westerly, 15, 20, 20. And quite often above the mixing layer, the wind will speed up. So right now, what you're seeing is a little bit of thermal activity upwind of the mountains. This is the west coast of New Zealand. Wind's coming off the sea. Guess what? This layer is not going to go over the hill at all. Because if it lifts, green for neutral air, hits the hill, starts to go up, starts to go up, so what you're doing, you're lifting this package of air, and if it was going to go over the hill, it'd be lifted up to here, and it would be here, and it would be way, way colder than the air around it. So it doesn't go up the hill. It's a sea breeze. If you have a shallow sea breeze, it'll wash up against a hill, and it will stop. So you've got a wind here, and it doesn't go up the hill. That's an extreme circumstance. This just behaves like cold water sloshing around and sloshing up against a dam. It just stops. We're lucky in New Zealand to see this happening. You can see it happening really clearly, and we've got big hills. Okay, let's have a smaller hill. We've still got a bit of wind, 20 knots or so. Let's make the hill, 1,000 feet high. Well, okay, if the wind's 1,000 feet high, sorry, if the hill's 1,000 feet high, the air mass can go up it, but it's not going to go from here upward. This is not going to flow up very much. Can't flow up very much. So I've done one extreme. Let's look at the flow then. Draw it bigger. Decent sized hill. And we'll imagine that the convective layer is only about this deep. So let's shrink the size of the T-phi-gram and expand the size of the hill. Let's say the convective layer, the mixing layer, is about that deep. The inversion is around the top of the hill. Now you have challenges, because what happens is as the air runs up here, it's getting heavier and heavier and heavier in relation to the air around it. Now, I say in relation to the air around it, you can see the Bishop is like an individual hill, right? So you can imagine the air coming up over the Bishop and doing this, and this, if there's an inversion, this air that's lifted from here is cooling at 3 degrees, 1,000 feet. The air here, the temperature profile got was adiabatic, 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 inversion, warmer, warmer, warmer. This is warmer than that. So this doesn't want to go over the hill. It's going up into an air mass that's too warm for it to go up into. So the nature of the flow, if I don't draw any thermals, the nature of the flow is like this. And it doesn't go up very far. And if you have a real hard push on the wind and a low inversion, then the nature of the flow is different. Again, if it's windy and you have a good solid inversion, then the flow will slow down here because this is blocking the flow. So here's a windsock, and here's a windsock, and here's a windsock. And what you'll see is, let's say we got 25 knots on the ground. Bottom of the hill, not much. Top of the hill, 35 knots. The nature of the flow is like this. It humps up where the wind slows down, and then it does that. Whiteboards are so difficult to keep clean. Now, when you fly in the mountains and you've got strong winds and tall mountains, this becomes hazardous. You're unlikely to thermal up the side of the Bishop. I mean, you might, but you're unlikely to do that for a pastime. But when you fly in big mountains, you quite often circle up the side of big mountains or figure eight up this. You're maneuvering. And you're maneuvering in not too unpleasant an airflow. But when you get here, suddenly the wind picks up You get the compression, what we call the compression. The wind here is much stronger than it is here. And you have problems. People will have said to you when ridge soaring, be careful about circling off over the back of the hill because you might get swept over the back of the hill, right? That's a given. Thank you very much. That's a given for ridge soaring. It's even more a given for mountain soaring, where you have bigger hills and you might thermal up the side of the mountain because you'll already be turning. But sometimes this part of the hill is completely benign. You can tuck in and just run up and down the sweet spot, or you can fly a circle, climb in away in a thermal, and you don't drift very fast. And sometimes it's anything but benign. It's really vicious. There's a big wind shear here. It's howling on the top of the hill. And there's not really any lift here. To test this out, let me draw the flow again. We were lucky enough at Amarama to have a visit from a guy called Larry Army, A-R-M-I, who's a professor of hydrodynamics at Stanford, I think. Lovely old guy, really smart. And we were talking about the flow. So he said you need to think about rivers. Imagine a riverbed and the top of the water here. Put a rock in the riverbed. Make the rock about 6 feet tall. The river's 20 feet deep. The river flows over the top of the rock. You can't see it. Now bring the river level down. River 10 feet deep. 6. No, make it 12 feet deep. 12 feet deep. The obstruction is half the depth. Can't really see it. Bring it down to about 9 or 10 feet deep. Once the obstruction is more than about 2/3 of the depth of the river, you will start to see the rock, the obstruction, on the surface of the river. You'll start to see it affecting the flow. And what you see in a river is this. I tried to draw a straight line there, apologies. So you see the river hump up in front of the obstruction, flow down the back, and then of course you know about waves and bouncing, and we'll come back to waves and bouncing. The atmosphere does that. If the mixing layer, if you say the mixing layer, the unstable layer, behaves like the water in the river, and the stable layer on top, where you're going to fly in the wave, is above the water level of the river, but you're in the river, what's happening to the flow around the mountain? Well, once the mountain is more than about 2/3 of the depth of the mixing layer, then you've got a real problem with the flow. And if it's windy, then, well, it would be windy, otherwise you wouldn't be flying on the ridge, would you? If it's windy, then that'll be the flow pattern. If you lower the water level still further, or lower the inversion still further, you might see that. What you've got here is lifting in front of the obstruction, the water, the river level dipping down quite rapidly behind the obstruction. And then if this layer is thin enough, you won't get a wave. The speed of wave propagation forwards through the flow is governed by the thickness of the flow and other things. And if the flow is really thin, you'll see the water come down here, and then it'll stand up in a hydraulic jump. And you can make a hydraulic jump yourself. You get a plate, I'll use a book. You get a plate and you hold it under a tap, and the water spills onto the water flows out of the tap and it runs on the plate. And you know what you get? You get a thin flow, then you get an oval or round circle of a wave jumping up around at the end of the flow. That's a hydraulic jump. You get to a critical speed where the wave could propagate through the gradually thickening flow, and it just stands up in a ring around the flow. So it flows out, and then you get a ring around it, and that's you can make your own hydraulic jump. You can't saw this when it's happening in the atmosphere because it's chaotic. You can saw a rotor, but a rotor has a pattern. You can't saw a hydraulic jump because it's chaotic. It's a chaotic flow. And yes, I've spent many happy hours in hydraulic jumps down at the bottom of, well, just down at the bottom of Mount Cook, for instance, in a howling westerly, just getting pounded and looking for a pattern and gradually going down because there's no pattern, so you can't saw it. We get some classic hydraulic jump situations at Amarama. It's really interesting. You're not likely to see that here, to be honest. But you are likely to see this flow situation where you've got a bit of wind, but the inversion is near the top of the hill and the air doesn't want to go over the hill. Right. Take a breath and review what I've been talking about. I wanted to introduce talking about stability in terms of looking at the T-phi gram. So we identified that the T-phi gram is drawn skew width, skew T, log P, to give you a representation that you can just look at and read really easily. It's clear, it's just laid out. They do it in the cricket. You know, you look at the cricket and they have these advertising placards laid out on the grass, and they're completely distorted. So it looks to you like that when you're looking at the, that's what we've done with the T-phi gram. It's the same principle. It just distorted it so you can see it. Okay, so the bottom layer, once you mix the atmosphere up, the dry air will be 3 degrees 1,000 feet, and above that, it won't be 3 degrees 1,000 feet. If the air is not stable, it will go over the ridge nicely. If it's stable, it won't go over the ridge nicely. If it doesn't go over the ridge nicely, then you're likely to find slightly rising air well in front of the ridge. And on the top of the ridge, the air's already going down. I did this in New Zealand just to prove it. We flew out in the wave. So look, we did this. Mountains, wave, blah-de-blah-de-blah. We climbed up here, flew out here, turned around and flew back to see what the air was doing in front of the first mountains, the big triggers. Now these are like 8,000 feet, the wind's 35 knots, and from about 1 kilometre in front of the hill, at ridgetop height, well, it was slightly above ridgetop height because obviously ridgetop height wouldn't have been clever because there's nowhere to land here. From about 1 kilometre out from the hill, steady sink, 2, 3, 4, 5 knots of sink, because the air was doing this, that, in front of the hill. Definitely, quite definitely. And here, we expect to find lift, sink. So, that's a really interesting experiment. It was quite obvious. And there was so much sink that having started reasonably high, I suddenly thought, this could go badly wrong. Of course, there'd be a little bit of lift here, and there were Qs and Qs and Qs and Qs and Qs here, so you're in the stable layer above the Qs. And you could get down here and you could soar around all day. The trouble is, 2 choices of landing place on the west coast, salt or fresh. That's it. So that was an entertaining experiment. So I wanted to talk about this because I wanted to illustrate that if you if you understand a bit more about the physics of how the day's working, you can understand a bit more about how to use the day and what you're likely to get, or you can understand what's happening now, and you can make inferences about, is what's happening now here going to happen over there? All right, so I've talked for 45 minutes or so. When do we start? 11. Okay, so let's just ask questions now, and then we'll come back and talk a little bit more about ridgeline. Questions on that?
I was going to say, Jack, I wouldn't sort of dismiss hydraulic jump. Maybe certainly in the mountains, you get hydraulic jump relatively often. It can be sort of incredibly rough, as you say, but it doesn't go all night, but it can be sort of.
My experience of the jump is that the flow might look like this, and in here is chaotic, but above here in the wave, you get a wave standing on top of that. So if you can just reach into the bottom bits of this, you can get up. But if you're operating in here, it's an absolute bitch.
And what we sort of get is a vertical face of the clouds, and usually there's 6,000 or 7,000 feet. There's nothing behind us, and it's incredibly turbulent, like rotor. You know, you can, if you've got big flappy wings on the Astro-5.
Yeah, well, I think
you can go if you get to the right.
I think you'd be going up the front here, wouldn't you? Like this.
I agree with Nick, because Colin Hamilton, I may have it on my computer.
We often get either wave or a hydraulic jump off the back of Bishop, off the foot in easterlies. Yeah.
Colin Hamilton's got some great photos.
Yeah, that's the one.
Colin about that. It may be, I mean, there is
Wave off the back because it's an ideal wave generator when
Yeah.
we're blowing from the east.
But there has been hydraulic jumps.
Well-
It's got a lovely. I can try and search it out if you like.
We'll find it when we have a
Yeah,
break.
yeah.
My experience was that if it's a hydraulic jump, it's not soarable. If it's a rotor, it's soarable. But if it's a hydraulic jump, if you can get in front of the jump, then it's soarable.
Yeah, I agree with that.
You get in front of the jump, then the air is
Yeah.
going up here.
Yeah.
If you're actually in it, but
No, once behind it, no.
I guess, G, but in New Zealand, I'm guessing now, you have to approach those hydraulic jumps from downwind, basically, don't you?
yes, you do.
Well, here we can come in from the side, basically.
Yeah.
Yes.
Or in
So
front of them.
Or front of them.
Yes.
So
If you get in front of it, if you can get in front of it, then you've got the wave runs up the front of this mixing layer is just sitting there with kind of chaotic random motion in the first bit, and then later on there'll be thermals in it. But right here is just a mess. Whereas if it's a rotor, then the shape of the flow is actually, it's a wave shape, and the rotor does this, and there's vorticity in this direction, and there is a pattern and a nature to the way the thermals are working in that, which is usable. But for me, the defining feature of trying to soar a hydraulic jump is it's chaotic. And that's the point about a hydraulic jump. It is chaotic. If you can actually soar it, you're not in the jump. You might be in the interface between the chaotic bit and the laminar flow. And that will be less chaotic, but it'll still be a mess. That will be a mess of rotor in the front of it, shear up the front of it. Anyway, look, it's real, it happens. This was a way of getting into discussing the air mass. This is a way of getting a handle on discussing how the air mass works, how it moves around, and how you can talk about it. Any more questions? Yes, please.
So I'm hearing that it's important to know the height of the inversion about the height of your hips, in which
Yeah.
So does the terrain and the shape of the mountains affect
Yes.
the height?
Yes, the terrain affects the height of the inversion. Very much so. If you have northerly, westerly, Well, northerly, you might get an easterly here, but if you have northwesterly or westerly, the air mass is coming over higher terrain. And that affects the height of the inversion by means of the Föhn effect, which dries the air out and raises the temperature of the air. So that alters the air mass profile. Also, land track, pure land track, the distance from the sea affects the height of the inversion as well. So as you get further and further away from the sea, the mixing layer gets deeper and deeper and deeper and deeper and deeper. So you'd be better off flying here in a northwesterly or a southwesterly than you would flying in a southeasterly, because it's just down the road to horrible cold wet sea. Whereas if it's westerly southwesterly, it's a bit further to horrible cold wet sea. And the North Sea seems to be particularly cold and wet. So yes, the land track does affect it. When they produce the predictions on RASP and SkySight and Top Meteo, in theory, the algorithms take account things like land track. They think about it. I mean, for instance, the T5 for today, yeah, that's not the T5 for today. The T5 for today on SkySight, that actually was completely automatic. On SkySight, showed an easterly, southeasterly underneath a westerly, which is clearly that SkySight understands that we're right next to the sea here.
What I found really interesting was the full diagram in relation to the height of ridge and where the west would be.
Yes.
Because occasionally you'll have this view you're with the western and the ridge, it's actually like two views in front of it.
Yes.
And you're sitting there, of course, up and people go, what is that? And you go, not 100% sure, it's just here.
That's what's going on. I mentioned right at the beginning that pressure and gravity are related, obviously. If you look at Bernoulli's theorem, you'll see that, I think it essentially states that the dynamic pressure, the total pressure of the flow is the dynamic pressure and the static pressure. And if you have a high dynamic pressure, the static pressure will go down. In other words, the speed of the flow and the pressure are related, and that's due to gravity. One of the things that happens when you have a flow around the hills is that when flow accelerates, it goes down. And when flow decelerates, it goes up. There's something that happens at Amarama, which is a fascinating example of this. Looking from above, river narrows, widens. And the wind blows up here, and there's big masses of hill here and here. The wind blows up here, and it channels through here. And as it channels through here, it accelerates. And then as it opens up, it decelerates. And this will happen with a water channel as well. You'll see it in a water channel. As it accelerates, the surface of the water goes down. It's what happens on a boat. You know, boat speed is governed by waterline length. And what happens when a boat moves through the water is you get a wave caused by the boat moving through the water. As it accelerates the water down the side of the boat, the water goes down. Or a bridge pier, where a bridge pier sticks into the river, it acts like a boat hull. You see the water standing up in front of the bridge pier, and as it goes round the bridge pier, it goes down, doesn't it? So if you compress the flow, the surface of the water will go down. Expand the flow, the surface of the water will come back up and wave like that. It happens exactly the same at Amarama, where the sea breeze comes up the river. You get a constriction in the flow. It flows fast between the ridges here. And then as it flows away from the ridges, you get a wave in the flow, downwind of the squeeze in the flow. When you get the air mass blocked by a ridge and the flow decelerates, it humps up. That's why the water over the weir humps up in front of the weir. It decelerates, it humps up. As it accelerates, it goes down. It's really important if you're flying in mountains in a strong wind to understand that an accelerated flow will dip. And we'll talk about that again when we talk about ridge soaring, and we'll talk about, you know, how the air flows around the hill and where the hotspots are. So, yeah. So I'm just trying to disseminate a bit of a language here. Stability, dry adiabat, inversion, the nature of the flow. All right, let's stop for a quick break. Come back in 10, 15 minutes.